Good day, everyone. So, today, my group members and I will be presenting our research proposal with the title TiO2, ZNO, and ZNS for degradation of dyes. Before we get started, let us introduce ourselves. My name is Nur Aisha Ardila binti Rudi Rukimin with the metric number at 6773.
Hi, my name is Nur Alia binti Bohan with metric number 84989.
My name is Nurul Awali binti Saha and my matrix number is 85334.
Dyes are chemical compounds known for their ability to absorb and convert electromagnetic radiation in the visible, near ultraviolet, and near infrared light ranges. When they come into contact with materials like natural and synthetic fibers or paper, they form a permanent bond, imparting color to these materials. However, the use of dyes, especially in large quantities, leads to environmental concern due to their toxicity, low biodegradability, and the intense color they impart to wastewater. There are three photocatalysts that can degrade the dye, which are titanium dioxide, zinc oxide, and zinc sulfide. Firstly, titanium dioxide. It has strong oxidizing power and chemical stability, making it is a promising candidate for photocatalytic application. However, it suffers from rapid recombination and photo-generated electron-hole pairs and limited visible light absorption, which reduce its photocatalytic efficiency. Secondly, zinc oxide has a wide band gap and exhibits photocatalytic activity similar to titanium dioxide. It also faces drawbacks such as rapid charge carrier recombination and limited visible light absorption. Zinc sulfide has the ability to absorb visible light, which is an advantage over titanium dioxide and zinc oxide. It has a narrow band gap and high recombination rate of photogenerated charge carriers, with limiting its photocatalytic performance.
Now, let's talk about the problem statement. So, TiO2, ZNS, and ZNO are three extensively researched photocatalysts. There are two main classification systems for organic dyes, which are based on chromogens and application purposes. Organic dyes that will be focused on are azo dyes, anthraquinone dyes, and phthalocyanin dyes because they are mainly used in textile industries. TiO2, ZNO, and ZNS are often used as an elemental or doped photocatalyst or even as nanocomposites with mixture of only two photocatalysts. However, there is less research about the photocatalysis efficiency using mixture of three photocatalyst nanocomposite. Therefore, a research proposal is needed to conduct an experiment to examine the photocatalysis efficiency by using the mixture of TiO2, ZNO, and ZNS nanocomposite.
Our primary objective is to create these nanocomposites with precise control over their morphology and composition. Characterization will involve techniques such as XRD, SEM, EDX to analyze the structure and composition. Finally, we will test the photocatalytic efficiency of this nanocomposite in degrading various organic dyes. The use of synthetic dyes in products like clothing and furniture has significantly increased in recent years. During the dyeing process, about 12% of these dyes become waste and 20% of this waste is released into the environment. The goal of dye degradation is to remove this dye from wastewater, breaking down into smaller molecules such as water and carbon dioxide. Photocatalytic degradation is particularly effective and sustainable. It uses semiconductor nanoparticles like titanium dioxide, zinc oxide, and zinc sulfide. When exposed to UV or visible light, these photocatalysts generate reactive oxygen species that oxidize and degrade dye molecules into less harmful substance. This method is preferred for its efficiency and minimal environmental impact.
The effects of dyes are significant, which impact both human health and environment. For human health, malachite green can affect human immunological and reproductive system. Secondly, rhodamine B can contaminate the drinking water and causes subcutaneous tissue-borne sarcoma, and for methylene blue, it causes high blood pressure, cardiac depression, and the formation of Heinz bodies, cyanosis, and jaundice, which are potential side effects of induced tissue necrosis in humans. For environment, it causes water pollution. This will alter the physical, chemical, and biological characteristics of water bodies. Next, ecosystem disruption. The presence of dyes in the water bodies can disrupt the growth and the development of aquatic flora and fauna. Dyes can accumulate in aquatic organisms, leading to bioaccumulation and biomagnification in the food chain. Lastly, dyes can inhibit the growth of algae, which are crucial for aquatic ecosystem. There are three types of dyes. Firstly, azo dye. It is characterized by a general structure that includes a diazo group and a chromophore. The diazo group is responsible for dye's color, while the chromophore is responsible for its lightfastness and stability. The example of azo dye include direct red 2, direct blue 15, and Congo red. Secondly, anthraquinone dyes. It derived from a molecule with two ketone groups on opposing carbons. It can produce a range of colors including red, orange, yellow, blue, and green. The color is determined by the type of substituent group added to the anthraquinone molecule. Thirdly, phthalocyanine dyes. It derived from a molecule with a central metal atom surrounded by 4 pyrrole rings. Phthalocyanine dye have excellent lightfastness, making them suitable for outdoor application and textile.
Photocatalysis utilizes light energy to drive chemical reaction, often to degrade organic contaminants. The process begins with photocatalysts absorbing photons from visible or UV light. This energy excites electrons, moving them to higher energy state and creating electron hole pairs with electron in the conduction band and positive hole in the valence band. These photo-generated electron and holes migrate towards the photocatalyst surface due to concentration gradients and electrostatic forces. At the surface, these charge carriers participate in redox reaction. Holes react with hydroxide ions or water to produce reactive hydroxyl radicals. A significant challenge in photocatalysis is the recombination of electron and holes, which release energy as heat or light, reducing photocatalytic efficiency. To mitigate this, forming heterojunction, combination of two different semiconductors with suitable band alignment.
There are many different ways to remove dyes. The first one is chemical treatment, which are electrochemical technologies and advanced oxidation techniques. For electrochemical technologies, the performance of the electrochemical approach is determined by the composition of the anode used, as well as stable anodes created by precipitating a thin layer of metal oxides on a base metal. Next is advanced oxidation techniques. The essential premise of AOP is the generation of hydroxyl radicals, which can be produced using hydrogen peroxide, ozone, photocatalysis, or oxidizing chemicals, as well as ultraviolet lights. Second one is biological treatment, which are activated sludge and biofilm reactors. Activated sludge is a dense combination of microorganisms that is mixed with wastewater in a reactor to aerate it under aerobic condition. For biofilm reactors, the bacteria in the biofilm break down the dye molecules when wastewater passes over or through it. The third one is physical treatment, which are membrane filtration and ion exchange. For membrane filtration, semi-permeable membranes are used in membrane filtration to selectively let water through while holding onto dye molecules. For ion exchange, more benign ions from an ion exchange resin are exchanged for unwanted ions in the effluent. And the last one is hybrid treatment. An example is advanced oxidation process combined with biological and physical treatment. To illustrate, ozonation or photocatalysis, which are AOP, are combined with biological treatments like activated sludge or biofilm reactors.
We are focusing on synthesizing advanced photocatalysts including titanium dioxide, zinc oxide, and zinc sulfide using various methods. To start, we employ the salt gel process for titanium dioxide. It begins by granting a precursor solution with titanium isoproposite and isopropanol adjusting pH with nitric acid, leading to titanium dioxide solid. After agitation and drying, calcination enhances its photocatalytic process. Next, for zinc oxide, via hydrothermal method, we mix zinc acetate with sodium hydroxide, initiate hydrolysis, and autoclave the mixture for crystalline zinc oxide. Lastly, zinc sulfide is synthesized salt-bottomally using zinc acetate and thiourea. This process, coupled with characterization using XRD, SEM, and UV spectroscopy.
For evaluation on photocatalytic efficiency, the light fastness of organic dyes determine how efficient photocatalysts are. Light fastness refers to a dye's ability to retain its original color and not fade when exposed to light over time. Each dye's light fastness will be assessed by exposing it to bright light for a length of time. Although materials can become discolored and degrade over time due to ultraviolet UV radiation, this is not always the case. Furthermore, visible light has the ability to do more harm than shorter ultraviolet wavelengths. According to Satra 2021, physical tests are commonly conducted before and after exposure to measure the degree of damage.
There are three parameters affecting photocatalytic degradation process. The first one is pH. The optimum pH for azo dyes is pH 3 to 7, anthraquinone dyes pH 6 to 9, phthalocyanine dyes pH 6 to 8. As for the photocatalysts, which are TiO2, it is slightly acidic to neutral, ZNO, neutral to mildly basic, and ZNS, the optimum pH is neutral to mildly acidic. The second one is temperature. The specific temperature range is typically between 120 degrees Celsius and 200 degrees Celsius. And the last one would be concentration. The concentration of the dye in a solution before irradiation will be used as the starting point for degradation measurement. For statistical assessment and design of experiment, the first one will be using the response to surface methodology RSM with Central Composite Design CCD created using Design Expert Software DOE version 13. So the diagram shows a quadratic equation which predicts the relationship between dye photodegradation and the individual components. Second one is the water quality index, which will be used to assess water quality. The six parameters used are DO, BOD, COD, SS, AN, and pH. The diagram shows the calculation for WQI and the classification of water quality based on the WQI rating. The third one is the light fastness of the dye. The light fastness of each dye will be measured by introducing the dyes under intense light in a period of time. So the diagram shows the photometer and the blue wool standards, which will be used to measure the light fastness of the dye. So the expected outcomes would be sol gel process, hydrothermal method, and solvothermal method can be used to synthesize TiO2, ZNO, and ZNS nanocomposite. Next, the synthesized TiO2 can be characterized using X-ray diffraction, XRD, scanning electron microscopy, SEM, and UV visible spectroscopy. Next, the synthesized ZNO can be characterized using XRD, UV vis spectroscopy, and BET surface area analysis. As for ZNS, it can be characterized using photoluminescence spectroscopy PL, SEM, and XRD. The degradation efficiency of the photocatalysis for different types of organic dyes can be determined using the light fastness of each dye.
Depending on the wavelength, the mechanism can occur in two ways, which is indirect mechanism and direct when exposed to UV and UV is chemically excited and release electro-hole waves which start from Redox reaction.
Good day everyone, we are going to present our proposal research proposal. Unit number 677.